Hello. So we're here ostensibly tonight to talk about this, which, as JB says, is the disting. This thing here. I get the impression that it might be good to go back a few steps because I could dive right into what this does in the context of a modular synthesizer, but maybe I need to kind of define what a modular synthesizer is and why that's interesting nowadays to some people. This obviously is a modular synthesizer. There are various kind of competing standards for modular stuff. As anything built of parts, there are a number of choices of those parts. This particular format is called Eurorack because it initially is based on a very old format for electronics on a 3U 19-inch mount with mounting rails, you can see, and back in the day you would have made cards which plugged into a backplane. So like industrial equipment back in 19 whatever had this format. And I don't know when, it's 20 years ago maybe, I'll just pull that number out of the air. A couple of guys, these are Dirtfer, whose name is on this, and independently a company in the UK called Analog Systems settled on this housing as a new format for modular synthesizers. Previously a modular synthesizer to most people would have meant a big Mo thing, which are based on much bigger modules. They're 5U high, much wider, use 1/4-inch jacks. There are even more formats than that, but this is the Eurorack format, and this is where much of the kind of explosion of growth has been just over the last few years in modular synthesizers. There's more manufacturers of this stuff now that I can count. Some of them big, some of the big players like Dirtfer are still here. With a huge range of modules, some companies which just have one product, and kind of people like me who I guess are in between with a range of products. Expert Sleepers as a company started from software. They started doing audio unit and VST plugins, fairly I guess the usual stuff like soft synths and delay effects and flanges and phases and all that stuff. But when I wanted to start my own modular synthesizer for my own purposes a few years back, I wrote a software called SilentWay, which is a way of using the computer and the audio path through the computer to control the CVs that drive the modular. And I presented that at the Hackspace a few years back, and these are my modules here that do that. In contrast to all that, this module that I'm talking about tonight is nothing to do with that at all. This is just a module like any other, in that it just does stuff to control voltages and audio. I kind of feel I have to qualify that because so many people know me for all this other stuff, which is really quite specific. This is just a module. Like any of these others, I mean, you've got oscillators and filters and envelope generators and drum synthesizers and sequencers and mixers and quantizers and whatnot. And the disting does a number of those things. So this is going to be very waffly unless I actually start doing something. I think kind of in lieu of preparation, I just brought lots of gear. So there'll be something we can talk about. And if you want to take this off later into a discussion of analog synths in general or my other stuff in specific, that's fine. Just by lieu of doing something, let's just play this video, which is kind of the 2-minute introduction video on the website for this product. You can watch it up here, right? This might be incredibly loud now. So this attempts to summarize in 1 minute 38 seconds what this does.
Hello, this is the Expert Sleepers disting. The disting is a 16-in-1 multifunction utility module in a 4 HP Eurorack format. It offers a number of CV and audio processors and some function generators like LFOs and VCOs. The included functions include things like a precision adder with octave shifts, a quantizer with selectable scales, a dual wave shaper, a sample and hold function, LFOs, including one that can be clocked from an external pulse, and 2 VCOs, one with linear FM and one with wave shifting. For a much more detailed look at all 16 of the disting's functions, please refer to the user manual on the website. Cheers.
Cheers. Raise a glass if we're going to say cheers. So that was that. You may be none the wiser. But let's get into something. Presumably everybody here is at least vaguely interested in hardware. So I'll tell you what, I'll pass one round. I'll pass a couple. This little bed of stuff. So there we go. So what this is hardware-wise, I can point out some key elements. There's another one here. It's all driven from this, which is a PIC32 microcontroller. That's running all the software, obviously, the firmware. This here is an audio codec, so that's it's stereo in, stereo out, digital audio, and that's streaming its digital audio backwards and forwards.
Could you say the letters there? So we've got IC4, IC1, IC2.
Oh, okay, yeah, sure. So IC7 is the PIC. IC8, the one surrounded by capacitors, is the audio codec. And then the rest of it is kind of analog stuff. I guess it would help if I pointed out the other components. So obviously on the front panel here you've got, there's 8 LEDs, so they're just connected straight to the microcontroller so I can turn them on and off. There's these 2 pots here. They're basically going into the analog to digital converters on the microcontroller to control stuff. This one here, the one marked S, is going straight to the microcontroller. This pot here and this jack socket, the effect of both of those is just summed and that goes into the controller. And then these 2 inputs and these 2 outputs are the ones that are going in and out of the codec. So X, Y are the inputs, A, B are the outputs. So in terms of the circuitry, you consider that this, what's that, IC3, these are all op-amps here, these ones basically. IC3 is mixing these things and doing some DC offsets. I don't know what that one's doing. Probably doing buffering the inputs. Another thing that might be worth mentioning at some point, which may as well be now, is you can see that the sockets light up. This is an innovation, nobody else has that. I invented that. I'm quite pleased with that. So there's what they are is translucent sockets, and if you look carefully, you can see there are some surface. You can probably see it easier when they're lit up. There are some surface mount LEDs underneath the sockets. So part of what these op amps is doing here are driving those LEDs. And this op amp here with all these passives around it is it's an output filter for the DAC. The DAC gives you a moderately noisy signal by itself, so you have to basically just put a half decent low pass filter on it to get rid of all the out of audio range crud. So that's a second order active filter, second order active filter on these 2 outputs here. And there you have it really. I mean, in terms of functional blocks, it's quite simple. Got a couple of voltage regulators at the top. The only voltage you can guarantee that you're going to have inside one of these cases is plus or minus 12 volts and ground. So anything that needs logic, which is a lot of stuff these days, you need to get your own 5 volts from somewhere, and indeed your own 3.3 volts for the microcontroller. So that's largely it. Hardware-wise, though we can go into any more detail you require. The interesting bit, I guess, is, I don't know, they might be interested to talk about why do this? Because after all, this is an analog synthesizer, right? And a lot of this is just 100% analog. There was an interesting observation, I don't know if any of you have heard or seen the documentary I Dream of Wires, which is doing the rounds at the moment. Somebody, I forget who, made the observation that an awful lot of modules nowadays are almost entirely digital under the hood, but they just have analog inputs and outputs. which is a great kind of lowest common denominator for everybody. If everybody just talks in terms of voltages, it doesn't matter what you're doing behind the screen. It could be analog, could be digital, could be both, could be going off into space and coming back again. As long as the voltage goes in and the voltage goes out, you're golden. And why? I mean, there are other modules which will do things with a like a proper DSP chip, whereas I'm doing this with a microcontroller, which might seem like a slightly odd choice. It was partly a kind of let's see how much you can get out of one of these things exercise. I mean, this chip in bulk is £1.50, something like that. That's composed to a decent DSP, which is going to be nearer a tenner. So that immediately makes it a lot cheaper. And the overall, this retails at £119, I think. And it would be substantially more with an actual DSP chip in. So that's the hardware. Should we? I don't know where to focus this. Should we talk about who's here is hardware, who's software, who's both?
Who's neither, I think, is a
Who's a musician? Who's a musician? Okay. Well, I mean, we can also purely talk about what it does in terms of what it does for music, if you like. But this being the Hackspace, I really wanted to focus on not trying to sell this because they're only on, you know. What I'm interested in talking about is because, I mean, basically it's why I thought this would be interesting for the Hackspace is because it's got this little connector on here, which is the debug and programming header for the chip. So, I mean, obviously I use that to program it when I'm developing it, but just with a little program, this is the program that I use. There are other ones. That's less than 30 quid. That's the Picket 3 from Microchip. All the software tools are free from Microchip's website. Basically, you get one of these, connect it to your PC or Mac, you can just plug it into the, I can see, because it's very dark, plug it into the board, and now you can program your own code on that, do what you like, which is kind of fun. So, what I have, at some point I'm going to plug it in and make it do something, but would that be a good thing to do first? Would it be a good idea just to have it do something so you can see it do something?
Yeah, I think that's a really cool.
Yeah? Okay.
Do a demo of your amazing Eurorack video, and it's always interesting to see the end result.
Yeah, okay, well we'll start with the end result and we'll go back to this. So what I have set up here is really far too much for a demo, but I just brought everything. This is my modular that I go out gigging with. So I have that here because I know that it's all plugged up and ready to go. This is just some other random stuff that I might need. And it's powering this module on a very long lead so I can wave it around. So let's just get some leads. Let's do some patches, because that's what modular's all about at the end of the day. So we'll get on to hacking it later. So this is powered up. So the top knob selects which of the 16 functions it's going to do, which is indicated by these LEDs at the top. Once you know what these 16 symbols mean, it's perfectly clear what it's doing at any one time. Until that point, there's a cheat sheet. Actually, what have we done with it? There it is. Some guy on the Muff Wiggler forum did this and put it up, and I've laminated it at home. It's awesome. So this is a potted explanation of everything that it does. So let's just start in the simplest mode. Mode 1A is the precision adder mode. So what this does is it just basically you've got your inputs. So every mode's got inputs and outputs. And that's kind of dictated by the way the hardware is. You can't hack the thing to have 3 inputs and 1 output because there isn't the hardware for that. So 2 inputs, 2 outputs, and 1 control thing, basically. I kind of interleave a demo in technical talk here. The codec is running at 72 kilohertz, I think. Which is not a normal audio rate. The reason for that is because the PIC is running at its maximum frequency of 40 megahertz. Microchip have since released one that runs at 50 megahertz, but this is the one that runs at 40 megahertz. And basically it's what convenient division of that can you get in an audio rate. And it turns out that it's about 72. So you can run that slower. I mean, you can clock the, if you want to save power, say, you can clock the PIC slower, you can clock the codec slower, and that will save power. But that's running at about 72 kilohertz. So these things, that's like proper nice anti-aliased audio at that frequency. The control input is being sampled by the ADC on the PIC, and that's being sampled at a lower rate. I think it's about, I should really know this, it's about kind of 10 kilohertz-ish. So you typically don't use that for a signal input, but you're welcome to. And all the processing, unlike in a VST or something like that, where you typically run on a batch of samples at a time, this is running its processing on every sample. So there's no buffering, there's like minimal latency. So, because one of the things that you often end up doing in a synth like this, because you're just plugging anything into anything, you might just plug audio into a control voltage input because they really are the same. So you expect everything to react at audio rates or above. Unlike a VST, whereas when you move a knob, you expect to hear stepping as the low uptake rate changes it. With this, you don't expect that. So,
just a quick question: what's audio rate? Like, what would you what?
Oh, a normal audio. So a normal audio rate would be like CD rate, 44.1 kilohertz. 44. Or 48 is another common one, and then double rate is 88.2 or 96. Yeah, I mean that's what it is. So this is higher than CD rate, not double rate, but in terms of what it's doing, it's fine. So yeah, this is the adder mode. So it's taking the two inputs, and that is giving you the sum, and that's giving you the difference. And into that mix is a voltage generated from this control, which is stepping through integer multiples of 1 volt, plus or minus 1 volt. So that's nothing, and that's indicated by these LEDs in a handy binary format, which everybody can read. So 1, 2, 3, 4. So as you can, because it's sum and difference, and that's taken into account, you go from 0 and then 1 volt, plus 1 volt, minus 1 volt. Plus 2 volts, minus 2 volts. Blue is negative, red is positive. And so if we actually patch that in, if I get this thing making some kind of noise, that's not the ordinary awesome noise in the world, but it will do for now. That's not amazing that. Okay, so that's the thing. So what we're going to do is, that's this VCO. So I'm going to take its pitch CV, which is coming from here currently. I'm going to run it into the disting. I'm going to take the output. I'm going to put it back in. So that, the pitch of this, where's my mouse? The pitch of this is now. You get the idea, pitch. So, because it's coming through here now, well, you can see the lights changing, which is nice. But if I use the offset now, because it's 1 volt CV, it's going up and down by octaves. And if I had another signal, well, this is naughty stuff, right? But it's all good fun. Let's take this. This is an LFO. Let's stick that in here. Attenuate that a little bit. Combining those two signals, and if I put that LFO on the Z, which is the octave shift, that's it doing something. So that's the absolute simplest mode, which is, you know, going through a 40 megahertz processor to add two numbers together is not necessarily the best use of line of traffic. It's convenient. A slightly more elaborate process, just by complete comparison, is the Echo one, which is 3D. So unlike those other two, unlike those ones which were, unlike that one, which was a CV process, let's just get that thing back. This is an audio process, so there's a 3D Echo. So if I take my so there's our sound that we're going to get pretty bored of pretty quickly. And what we'll need as well is a clock, because this is it's an echo. If I turn this feedback on, you can hear it's doing something, but the time of the echo is linked to linked to a clock input. So let me just punch some holes in this. Okay, so that's, you can hear it. So obviously you can hear it's an echo. So this control in here, which you see in all this, is like the combined feedback and level. And you can see the delays are in time with the clock pulse that is being plugged into here. So fine. Yes?
Yeah, just ask you a question about the whole system. So if I understand correctly, we have signal coming in from the laptop, from Ableton Live, going to disting.
No. So I'm possibly confusing the issue by using the laptop at this point. I'm using my software that controls the modular. So all the laptop is doing at this point is generating the pitch, CV, and the gate for the synth.
Okay.
I mean, yeah, I guess I could completely take that out of the equation if it would make it easier to conceptualize what's going on. But I'm so used to using this because I made this for my own purposes. So, so let's clarify that. All this is doing at the moment is driving this sequencer. Okay, this is basically a sequencer. I've got pitch and I've got a gate, and that's all that's doing. And then that is, I've got a little synth voice patched in here, VCO, filter, VCA, envelope, envelope's coming from there too. So when you're hearing it by itself, all that this is doing is firing off a gate there. In fact, you can see it here, look, there it is. Okay?
Yes, I guess that was what I was struggling to really understand is what is the in that comes to the disting and what is
in this patch, what's coming into the disting is the audio.
Okay, got it.
So this is the input to my mixer.
Okay.
And if I plug that into here, that's the signal. Okay, so what I've done, I've taken that audio signal and I've plugged it through the disting.
And now
the disting is processing audio.
Yeah, okay.
In the previous patch, the disting was processing the CV, but now it's processing the audio. Okay. So I guess this is kind of making the point. It's all just voltages, right?
Yes.
One happens to be moving a bit faster, so we call it audio.
I think we have a range of experience.
Forgive me if I go too fast. I kind of live and breathe this stuff. So, So this was the echo. So the thing is echo, and the time of the echo is being driven by this. And And that's super handy in a kind of a standalone modular where everything's sequencing itself and it's all running off its own clock. To have an echo that's actually in time, it's actually quite hard to do, because otherwise you're sat there with a knob twiddling the delay time, trying to get it exactly right. If you can just plug a clock into it, you go. So I guess that what I wanted to show there is the kind of the range of capabilities, from simple CV processing on the one hand to really quite elaborate audio processing on the other. And it does 14 other things, any of which I could go into if you're interested. But I guess that kind of shows what's going on.
Is it fair to say that the main difference with other modular synthesizers is that it takes audio and CV?
Not really. The main, I mean, the thing that sets this apart really is the fact that it does so much in one small package. It's taking advantage of the fact that it is working in software, and all you have to do is switch the software and you've got a whole new function. I mean, any module will take CV or audio in, like I say. It may do something more or less useful with it.
Yes. So perhaps if we were to go back to a very basic template of a modular synth, we have some signal that's generated by a module. Perhaps it's a sine or waveform in its simplest form. Then the signal would go to perhaps an LFO to modulate that signal, or
Well, we could. I mean, let's do modular synth 101 then, shall we?
Yes.
Modular synth 101 or analog synth 101. Sorry, I kind of assume you've been
I suppose we have some experts in modular synth. We have Tom here who knows really well, but then the rest I think has a different range, and we have.
Well, let's go right back then. So. As I said, the patch that was making that sound that you heard starts with this oscillator here. This module here is a VCO, so it's a voltage controlled oscillator. All it does is output a waveform. And if I get, I'll tell you what, I'll stick an oscilloscope on.
Yeah.
That'll help. Okay, so this is the input to my mixer, and I'm going to plug it straight into the VCO. Turn it down because that's really annoying. But okay, there you go. So that's all it's doing. It's just going beat basically. It's got a few different outputs. So it's got a triangle wave, square wave, pulse wave. Yeah. That's all it does. It just sits there and does that forever. And then if you wanted to do something different, you use a control voltage. So the normal one that you would use first of all is this. Oh, it's really annoying when it's so loud. Use the control voltage input, and as JB said, if you just stick an LFO. Pitch goes up and down because this is outputting another waveform at a much lower frequency, which is just going up and down, and the pitch goes up and down. If you want to play a tune, then you need to generate a sequence of pitches that correspond to the right voltages, which is what this software was doing here. And now I'm confusing the issue by introducing software again, but all it's doing is generating voltages. I mean, I hate to say this, but it makes it easier to think of it in terms of MIDI. A lot of people would use a MIDI to CV converter because that's familiar. Basically, this is just a MIDI to CV converter, but in software, right? It's not even MIDI anywhere in here, but just think of it like that. This tells us the notes. The notes generate a voltage, which comes out of this socket here. And that's plugged into the oscillator, and then the oscillator changes pitch to play the notes that you want to play.
Just a quick question on that.
Yeah.
Are there standard voltages for pitch?
The not absolute voltages. The standard is, for most things, is 1 volt per octave.
1 volt per octave.
So a change of 1 volt gives you a change of 1 octave. Now, what 0 volts corresponds to is completely up in the air.
Okay, well,
and some manufacturers try and standardise that on like C3 or something like that, but there's no standard for that. The standard is what happens when you change the voltage.
Okay.
Yeah, so most things in Eurorack run off that. Buckler synths run off 1.2 volts per octave, presumably because then a tenth of a volt is semitone. But 1 volt per octave is kind of easier. And then some old vintage synths and some modules like LFOs in Eurorack run off a different thing, which is rather than the exponential volt per octave scale, they run off a hertz per volt thing. So the frequency is linearly related to the voltage. But that's really hard to work with, because then if you want to go from like 100 hertz to 200 hertz, it's however many volts. If you want to go from 200 hertz to 400 hertz,
it's different.
It's just really weird scale. It's really hard to work with that. So pretty much everything runs off 1 volt per octave. Yeah. So that's the VCO. So what happens in this after that? Let me just define. Let's just turn that up so it's not. Well, so the classic patch is a VCO, or the basis of the patch is an envelope generator, and you would often get a hardware envelope generator. I'm using a software one, which is driving this VCA, voltage controlled amplifier. So now the sound isn't always on, it's being controlled under voltage control by the amplifier, and the shape of the envelope in this case happens to be coming from software, but often would come from a hardware module which is listening for the trigger pulse and then generating the ADSR contour or whatever. So if I give that a bit of release. Okay, and then the other thing that's patched in here normally is a filter. So ignore this one. This one is a filter, it's certified. That's what you want for an analog filter. And again, the filter frequency is all voltage controllable, so I think in this patch I've got the filter frequency patched into an LFO, which is coming from here. So when you combine the filter and the VCA and the envelopes, you've got a very, very basic synth voice, which you can use to play tunes or make horrible noise, depending on what you want to do. I have this module patched in, which makes horrible noise. Where's my mouse? So you get the idea. So you can go from one extreme to the other. So that's the kind of environment this module is living with it, I guess. And its functions were chosen. The functions as programmed were chosen to be 16 different things that you could do with 2 inputs, 2 outputs, and a control signal meaningfully, and would be useful to everybody. Certainly to people with the clockable delay that I just showed you, for people who don't have software plugins for things to be in time and stuff. But generally, there's anything I can think of that would fit the hardware format once the hardware format was finished. Because one thing this doesn't have, for example, is an envelope generator. Because for an envelope generator, you really want lots more knobs for attack, decay, sustain, release, whatever. And I've only got one knob, so I can't really do that. So everything it does has to be something where one knob is enough. So if I get the cheat sheet back up again. So I showed you the adder. The second one is a kind of VCA ring mod / ring mod thing. So that's basically a multiplier, right? It's taking two signals and rather than adding them, it's just multiplying them in the mathematical sense. Which is basically what a VCA does, or what a voltage controlled amplifier typically is a it's a one quadrant multiplier, because typically one input only has positive signals in it, so that's the envelope. So you've got your audio signal, which is positive and negative, and you've got your envelope, which is only positive. So you're kind of multiplying those two to make your sound louder and quieter, which is easy enough to do in hardware, in analog hardware with a VCA circuit. What this does, which is spectacularly easy to do in software, but less so in hardware, is a 4-quadrant multiplier where both signals can be positive and negative. So if one is an audio signal, one's a control signal, if it's positive, you've got your normal envelope. If it goes negative, then you're inverting the signal. And if both signals are running at audio rate, then that's basically what a ring modulator is, if you want to sound like a Dalek. So again, I guess I could be. Maybe I should bring up the 38-minute video which goes through every mode of detail with audio samples. But that's a good example of something that's very easy to do in software, which is less easy to do in hardware, which is multiplication. Again, all these are kind of simple math functions. Rectifier is basically a absolute value function, minimum and maximum, very easy to do in software. This one is an interesting one, linear to exponential converter. Quite hard to do well, easy enough to do in hardware, but very, very sensitive to temperature changes, because it involves using I'm going to embarrass myself on the internet now by not getting this right. It typically uses a transistor junction in its exponential range, which they all have, but they're very temperature dependent. So you end up with like oven circuits and things being in thermal proximity with gum holding them together and stuff to get things stable. Whereas that same it's a very easily expressed mathematical function, and to do that in software obviously it isn't temperature sensitive because it's software. So that's quite an interesting case of something that's easy to do in software, or equally easy to do in hardware, but doesn't have the hardware problems.
What happens if you use to change the temperature of the circuit?
Of this circuit?
I mean,
if you change the temperature of a hardware exponentiator, the scaling goes off, and what used to be, so typically it's what you have on a 1 volt per octave CV input to turn an exponential signal into a current usually, which is what you need to drive the VCO. And if the temperature scaling goes off, then you no longer have 1 volt per octave, you have a different number of volts per octave. Or just the absolute pitch goes up and down.
So you could mess about with it, just putting your thumb on it or something like that.
Well, maybe not your thumb. Yeah. So this is the classic problem of old synthesizers going out of tune, right? This is why they go out of tune, because they've got things that wander under temperature. Blah 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 blah. Yeah, a bunch of stuff. Yeah, the last 4 LFOs and VCOs. So one of the modes of this thing is actually a VCO. So if I just take my audio output and plug it into here, that's my VCO. It's just a VCO. 1 volt per octave input. So I could, in this patch I had going, I could replace this with this now and it would be an oscillator, which is kind of handy. And it's got some LFOs which would do that if I stick it into LFO mode. You can see the voltages changing more slowly. So that's kind of the things it does. Who wants to see the software? Is anybody interested to see that? You're interested to see the software. I'm not going to show you the actual software, but I'll show you the software that you can get off GitHub. So this is how you hack the disting. Like I say, you need a disting. You need a Picket 3, which is the microchip development tools, which plugs into the header here. You need MPLab X, which is the IDE, download from microchip.com, and you need the 32-bit compiler, again, download from microchip.com. The compiler has a paid-for mode and a free mode. I'm using the free mode. Seems to work. At the end of the day, it's spitting out MIPS code under the hood, so if anybody used to work on PlayStation 1, they'll feel right at home. Raise your hand. Yeah, it's amazing how branch delay slots come back to you as a thing you wish you didn't have to know about. But, so that's all you need, basically. And then the software, if you refer to my website, you'll see it there. I've got a repository on GitHub, and I've got this little project I've called Hello Disting. So if I just make a copy of that right now, and then we'll open up the project in MPLab. File, open project. Where did I put it? Where have I put it? Where am I? Right. Okay, try not to look at all the project names that I haven't actually released yet. No, not that one. Come on.
Too far away anyway.
Yeah, no, oh no, you didn't all see that. Damn it.
Trying, but they can't see anything.
There we go. Okay, hello disting. So, navigate down to the .x file, which is the project for the thing you just downloaded, and open it. And what you will have is this. There's a header file with some constants in it, and there's a main.c, and there's another file which does the I2C functionality for talking to the codec. We don't need to worry too much about that. So the way this is structured, basically, I mean you can't see it, but you can go, once you've downloaded it, you'll be able to read it.
Would you make your screen bigger?
I should do, I guess. What do you mean, go into a slightly...
So what kind of code are you writing? You have to write
C. It's C.
It's in C?
Yeah. Well, you can write assembly if you like. Sometimes it's worth it. I mean, bear in mind you're running on a fairly... I mean, it's a 20 MIPS processor, right? So every cycle counts if you're processing every sample as it comes in. So there are cases where you might want to go to assembly. Especially for multipliers, because there's no floating point.
Oh right.
So you're into fixed point maths, and the brain dead thing about C that anybody who's ever thought about it is that you can't multiply properly for hardware in C, because what you want is to take two operands that are one length, multiply them and get an operand that's twice as big. Whereas in C, the result of the multiplier is the same type as the result of the operand, which is completely messed up, because that's not how life is at all. So when you've got hardware with a one cycle 16-bit to 32-bit multiply, you can't express that in C. You just can't. There's no way in the language apart from doing ASM open bracket. So you may want to do that. Can you read that better now, maybe? I can't see anything anymore now, of course, but...
So is it all, you say it's all integer? No.
Yes. So I guess I forgot rid of this window, that would help. So this is basically the main file. There's a bunch of includes, boilerplate stuff. Hash pragma config is microchip pick stuff. That's how you set up what's known as the configuration words, which are areas in the flash memory that are configuration registers that are written during programming and are not writable at runtime. So there's a bunch of cryptic stuff in here. If you download the compiler manuals, there's big PDFs for every single microchip pick, of which there are thousands, which include the things you can express here. So the things that we're setting up here primarily are the system clock and the peripheral clock. So, like I say, it's running at 40 megahertz, so you'd have to believe me that that's what this is doing, basically. It's using a PLL. I guess that might be worth mentioning. There's no crystal on the board. It's running off its internal fast RC oscillator, which is spec to run at 8 megahertz to a resolution of about 1%, to an accuracy of about 1%, I should say. Which is fine. It saves you some board space and some component cost. You can't always do that. If you can get these parts with USB on state, and then you do need the crystal because you have to hit 48 megahertz exactly for USB. But for this, where it doesn't really matter how fast it's running at more or less 8 megahertz, and then it's using the internal PLL to multiply that up to 40 megahertz, which is what all this gobbledygook here is doing. And there's another central clock in a PIC, which is the peripheral clock, which is clocking all the peripherals. So I imagine peripherals being UARTs and I2C and all those bits that hang off the main MIPS core, and you can have that running at a different rate to the system clock, but in this they're running at the same rate. JTAG off, just not using it. Okay, and now we're into some interesting variables. So these are kind of the core things that are doing stuff in this simple framework. So this one is time. So every time the codec gives a sample to the PIC, that goes up by 1. So that just lets you know how much time has elapsed. Ideally you want that to be going up 1 every time you see that number, but just in case it's not, it's there. We'll get to it in a minute, but the audio, the codec is coming in through an interrupt and writing into these registers, which is why they're volatile. So that's throughout the code, that's the inputs. And then the main body of the code writes into these out registered memory locations, and then on the interrupt, the codec writes those out. So that's all that's doing. There's two other, as well as the 2 ins and 2 outputs, the 2 things that we've got are the 2 control values. So selector, which I should have written called bow or something like that. It'd come up with some form of reverse Hungarian that starts with bow. That is this pot here basically. So the ADC on the PIC is a 10-bit thing. So that has a range of about, well, it's 0 to 3FF. If it goes over the whole range. Yeah, and then the pot, the one that's called pot, is this pot, which is the effect of that pot combined with the signal on this input. And that's read every now and again, and that's just a dummy variable for a delay loop. So it doesn't get optimized out. So delay loop is used mainly at startup, so try to unplug that. You see it, when it boots up, it just does a little light show to let you know what it's doing. So that's when you might need a delay. There's probably more elegant ways of doing that, but that works. Okay, this function, which is called on every update, is reading the ADC channels for these 2 inputs here. I won't go through every line, but basically it's reading the pots. If the selector has changed, it sets a flag, so it knows it has to change algorithm. Obviously, if you're hacking this, this doesn't have to be an algorithm selector. You can make that anything you want, but the framework I provide has that set up. And also, that's something I haven't mentioned. There's a push button on the board itself. which is used in the factory to kind of initiate a calibration routine. So typically the user never needs to press that, and if they do, they have to run around screaming for a little while to get back to normality. But if you're hacking, you can do whatever you like with that. It's just a button on the board. So that's what that one is, and then this is the comment says an archetypical algorithm loop. So in the actual code for this there are 16 loops that look a little bit like this. So there's a boilerplate setup macro, and then it's a wild one. Wait for a new frame of audio, grab the values from the memory locations, do stuff, write the outputs back into the locations that are going to be picked up by the interrupt, and then boilerplate loop end, which may or may not read the ADC if it's ready, and that will be the thing that breaks out of the loop if you want to switch out. So that's basically it. So in terms of actually doing stuff, all you need to do is put some stuff in here and you've got stuff, you've got things going. I downloaded this, there's one guy at least who's doing stuff on the net, and I downloaded a bit of his code that he did, which I've never compiled before, so we'll try that in a minute and see what it does. I suspect it will make an unholy noise, but we'll try that later. So that's an algorithm. This function here is the code that generates that startup light show, just so you can see how you might want to do that. And it also is a handy crib sheet for the port locations on the PIC to write to light up the LEDs. You can control them all, in any combination. They've all got their own line out of the PIC. If you want to display any information you like out of those. So like I say, normally that's just showing you the algorithm, but for example in the offset, once you start changing the offset, it's showing you the offset in voltages. On the clockable LFO, whichever one that is, that one, again it's showing you the multiplication or division of the clock rate that you're using in a similar binary way. But you can use those for whatever you like. So that's that one. Okay, now we've finally got down to main, which, being C, of course, has argc and argv. Where argc and argv are going to come from on a PIC, I don't know. It's not as if you've got a command line. I don't know what could ever get to that, but there you go, it's there. What does this do? Okay, it does some system config. That's a PIC library function. I don't know exactly what it does, but you seem to need to call it. Turns on interrupts, sets the PCB, sets the button as a digital input, configures all the LED channels as outputs, runs the thing to flash the LEDs, jumps off to configure the codec. That's all in this other file here called i2c.c. And this is just copied off one of the microchip I2C samples. It sets up the lines as an I2C bus and squirts the data words down to the codec to do stuff. Specifically what that does in this case is that it turns off the high-pass filter, which is on by default, which means that it's now got DC coupled inputs, which you need if you're going to process CVs, because otherwise everything just decays off to 0, which is not what you want. And just to make the hardware a little bit easier, I've made use of the phase invert on the codec, because it was just more convenient to use an inverting amplifier on the output. So if you invert it on the codec, then you don't have to worry about inverting the values in software. So it's just making use of what you've got to avoid some other expense. But if there's anything else you want to configure on the codec, then you can do it here. You just need to send I2C packets. Does everybody know what I2C is? I2C is IIC, so they abbreviate it to I squared C, which is actually more syllables, but yeah. So it's a two-line. It's a two-line protocol for connecting up chips on the board, basically. Multiple host, multiple slave thing. You get a lot of stuff. The PIC supports it in the library and in the hardware. It's one of the peripherals I was mentioning earlier. So in terms of writing stuff on the PIC, you just have to set it up and send the values to it, and it deals with all the hardware of handshaking and sending it off to the thing at the right rate and whatnot. So that's good. So once we come out of here, the codec is up and running. And it turns the I2C off because we're not using it anymore. Flash the LED again to let us know we're up and running. Okay, this next chunk of code sets up the ADC channels for the pots, basically. And there's a whole load of stuff going on there that basically turns it on and sets the rate at which it's sampled. It samples 2 channels alternately, automatically, continuously. Basically, these PICs are so incredibly flexible. Just choosing the mode you want can sometimes actually be this much code, but once it's running, it's just doing it. So that's setting up the ADCs. Okay, the next block is setting up the I2S channels, which stands for, what does I2S stand for?
I don't know, job?
It's I2S. It's the digital audio protocol. I2S is stereo, IHS is 8 channel. That's the lines that it's going to send data back and forth between the codec and the PIC. So the I2C is the configuration, the I2S is the actual data. In PIC lands, it's the SPI peripheral, which is another 3-letter abbreviation. I don't know how interesting the system will be. SPI is another inter-chip protocol using 3 lines rather than the 2 of I2C. And on a PIC, it's the SPI peripheral that is co-opted to run the audio, basically, because it's pretty much the same. So this is setting that up. So you need 3 outputs and 1 input. The outputs being a word clock, which is the thing that's running at the audio rate, so 44.1 or 48 kilohertz and whatnot. And then there's it's not a bit clock. No, there's 4, that's right. There's 3 clocks in the digital audio. There's the word clock, which is the thing running at 44.1 kilohertz. You've got the bit clock, which is the clock that's streaming in the bits within those words. So typically that's running at 64 times, say, the word clock, because you've got, what was that, 128? 32. Some multiple anyway, because in each word you've got the audio bit. So in a 24-bit digital audio stream, you typically pad that out to 32 bits because it's a power of 2. And then that's your bit clock. And then you've also got the system clock, which is what is used by the codec to clock its decimation and anti-aliasing filters and stuff, and that's running way high at, I think, 128 times the word clock. In this it's running at 12 megahertz on. And the PIC's generating all those clocks for you, so you don't have to worry about that once you've set them up. And then finally you've got your data, your serial data out and serial data in, which you're actually transferring the data. So like I say, I'm explaining this, but you would never need to change that, because if you change it, it won't work anymore. So, but it's good to understand what these things are doing in case you want to go make your own thing that does something similar. So that's, as I say, setting up the SPI peripheral to do I2S audio in and out. That's the system clock, like I mentioned, that comes out of another pin. That's, again, configuring the SPI to run 24-bit, enable audio mode, enable I2S mode, and finally turn it on, enable interrupts from the thing, and then what that is doing there, SPI chan.c is actually sending the first word of data that's going to go out to the codec, and that is the thing that actually kicks the whole process in motion. So from then on, the PIC is constantly squirting out data, the codec is constantly receiving and squirting data back, and the PIC is continually getting interrupts and receiving that data. And the fun thing about that is that you get an interrupt for left and then right, left and then right, and there's no indication of which is which, so you have to know that you start the right one and that you always remember where you've got to. Because if you miss one, then you're fucked. So it's always been kind of amazing to me that it will just sit there quite happily at whatever rate and just always get it right. Unless you break in the debugger, and then of course you've mucked up the timing, and then you might restart the debugger and your outputs are swapped, which is confusing the first time it happens to you, but that'll be why it happens. The debugging on this is actually quite reasonable. It's not the fastest, but you can set breakpoints and inspect the values and inspect the memory. It's okay. And then finally, once we've done that, main loop forever. Switch on the algorithm that we're going to do, if there's only one, do it until it breaks, go back round, do the next algorithm. That's that one. And then this is the interrupt handler that I've been alluding to. So the interrupts on the PIC are really quite flexible. You've got any number of different priority levels and things that can generate interrupts, and on this it is just the I2S that's generating interrupts. And then basically the code reads, if it was a transmit interrupt, what's that doing? Oh yeah, if it's a transmit interrupt, then send 1 byte to either the left or the right. And then this is a static that just flips between 0 and 1 on every interrupt. So 0, 1, 0, 1, and then time plus equals that, so the time is either advancing or not, depending on whether it's left or right. Clear the transmit interrupt. If it's a receive interrupt, because it might be both at the same time, read the raw data in from the SPI buffer, and then sign extend for convenience, because the data you get in is 24-bit audio in the low 24 bits, which is actually assigned to 24-bit value, but you can't do 32-bit maths with that because you've got zeros in the top byte. So sign extended, so the rest of the code doesn't have to worry about that. And then stick it in these things that we're using everywhere else, and clear the interrupt, and we're done, and that's it. That's all the software. So like I say,
Really compact. There's not much there.
No, relatively speaking, to get it up and going. I mean, that's the joy of the PIC, really. Once you've figured out what the heck you're trying to do, and which of the thousands of options are the ones you want, actually getting it to do it, it's quite straightforward. Which is why it's great having examples like this on the web that you can just grab, because I mean, some of these things I just got from the microchip samples, or some of them figured out myself, but there's sample code for most of it if you know where to look. So yeah, and then once you've done that, like I say, you make sure it's plugged in. Board power, this is plugged into USB, and then you, with this as the main project, you do this one, which is make and program device main project, and this will go and build it, and it will program it, and let it run. Oh, I should load up the output window at this point. So it will. This is an interesting thing, I guess. So it gives you a bunch of stats of what's going on. That's just so it's programming. Yeah, it's finished. It's booted. Run the reset sequence. So this is telling you the name of the device that you're using. It's a PIC32MX150F128B, which is it's a PIC32MX, 150F tells you, the one tells you it's not the embedded USB host, it's the other one. And the 50 tells you it's got the most amount of flash. It goes 110, 130, 140, 150 or something like that. And the 150 has 128 KB of flash and 32 KB of RAM, which is the most that's currently in production. I believe there's one on the drawing board with more, but it's not available yet. The F128 basically tells you the same, and the B tells you it's the 28-pin version. You can get the same part in 2833, I think, and 44-pin packages, which differ only in the number of I/O ports they have. So this is the 28-pin version, and the 28-pin version comes in DIP, SOIC, SOP, and another format, DFN, I think. This is the SOP, the small outline shrink, small shrink, something. It's the smallest one, basically, because it's quite tight on the board. One thing about general comment about designing Eurorack modules. This is kind of the old school way of doing it, to have the panel like this and to have the PCB like that. A lot of these ones, a lot of the more newer ones, like if you can see here, like this one for sure, that one, they've all got a panel and then this PCB is parallel to the panel behind it, which is great because it gives you a lot of flexibility in terms of where you put your controls, and it makes it very shallow. And there's a big fashion for really shallow cases that these things slot into. But like I say, this is the old school way of doing it. All these Dirtful ones are built in exactly this way. They've got all the jack sockets in a line, all the pots in a line, because there's PCBs behind that in a line, which I find more convenient, to be honest. And it means you can make very narrow modules. Because if you had, there's a lot of circuitry going on there. If you had to have that, you get some of these. Where is it? There's like this one here. I think it's got 2 or 3 PCBs stacked up, parallel behind the panel to get all the stuff on, which is a bit of a bother. And also these jack sockets, they work that way. They're not vertical mounting ones. They're sort of on a bit of a tangent there. So this is now running that algorithm that we did here, which is a simplified version of the adder and subtractor, really. So if I get my LFO, I think it's running. Is it running? There we go. So there we go. So there's only one input, so add or subtract from 0. So 0, that's add and subtract 0. It's obviously going to be the same 1, and then they're now opposite because it's the inverting input. So that's just that. So there you go. So from there you can do what you like. That is using this. That's what I was talking about. I was talking about these stats. Why is that? No, that's interesting. There we go. That's what I was after. Right, let's do that again. This is extremely useful information. So this is how much flash is being used, and this is how much RAM is being used by your chosen algorithm. So as you can see, all this boilerplate and this tiny algorithm is using 7% of the available flash memory. It's using 0 bytes of RAM. There is no, that can't be true. No, it's using 0%. It's using 40 bytes of RAM of the available 32K, which is not a lot. So that'll basically be this stuff up here, the kind of the time, the in and out, and the selector, and a few others. The actual disting, the actual production firmware is using a lot more program memory. I forget how much, but it's got all of the data memory allocated, and that is almost entirely because of that delay effect. Obviously it needs a big audio buffer to echo. So that's using all of the available RAM. I mean, being embedded hardware, this is a completely different mindset that you have to get back into if you're used to just writing your code and every time you want an array or a variable, you just declare it and you let the computer figure out how the hell it's going to find space for that. In embedded hardware, you control the hardware, and if your 16 different functions all want 32K RAM buffers, they can all have them because they can just all be in the same place because they're not being used at the same time.
While we're at it, I have a DSP background, so I'm quite interested in some details about this processor architecture because I don't really know it. You already mentioned that it's a 40 megahertz.
It's a MIPS. It's a MIPS. The data sheet is the place to go for this.
Yeah, I didn't do my homework.
No, it's okay. I mean, there's probably some pithy information I can.
I mean, what I'm interested in is kind of from DSP point of view, like.
Oh, I see.
It's
There is no DSP.
Two cycles for an integer multiplication. So what I'd like to see like how many cycles would it take to implement a single bicot filter, for example?
Oh, right.
Just to see the DSP capabilities of this platform.
If you're going to do actual DSP, I don't know, you probably want to use a DSP chip. I mean,
you can generate signals from it. I could consider that as DSP as well.
That's possibly the most salient information. If you've got 16-bit data, then you've got a single cycle multiply add.
I see. So 32 bits is 2 cycles from multiplication.
Yeah.
And so for addition, is it the same?
I think everything else is going to be single cycle.
I see.
Let's see.
So it's really boring.
So
It's cool, man.
This is really.
No problem.
I wanted to know as well.
I didn't go away and read this stuff before. I just kind of cracked on, really. But
single cycle apart from this 30-bit multiplication, basically, and
that's what I want to think, but that may or not actually be true. I'm sure there's some pipelining going on.
Yeah, that would have been my other question: how deep the pipeline is, and what is the cost for a branch, for example?
A branch is. This is one of the odd things. A branch is 2 cycles. In actual fact.
Whatever happens.
Okay.
Because there's an instruction that goes after the branch, which is executed before the branch is taken. So branch is 2, but I should really know this, if only from PlayStation. I'm sure the information is there somewhere, but I think it's. I'm just going to get it wrong if I say it. It seems pretty reasonable.
And the memory you mentioned that it has a 32K, 32 kilobytes of RAM. Is this shared between code and data, or
No,
is it only data?
code. Well,
Or the code runs.
the way I'm running it is the code is running out of the flash.
I see. So you can use for whatever you want.
I
The 32K is just
Yes.
is only yours.
I believe you can put code in the RAM and execute it. I might be making that up.
When you have enough flash to run code, I'm more interested.
I know, but
in
it might be
data,
fun to do that, right? It might be fun to algorithmically generate some code.
So you mentioned you're running cycle-based algorithms mostly.
Yes.
For minimal delay. Does it really make a difference if you have a few milliseconds delay in an analog, a modular setup like this? I usually have experience with that modular systems.
It's not. The latency is a bonus. I mean, in general, you want as little latency as possible because they all add up, right? And a real analog thing is instantaneous. It's mainly for the kind of the throughput and response, so that every cycle, if something changes, you get a. I see what you're saying. What's the correct answer to that?
The reason I'm asking is because I guess you can have a massive gain in terms of CPU performance, even if you run it on every 24 samples, say, because of the loops.
Yes, absolutely.
Management.
No, this is definitely true. but the latency.
So you can't tolerate it, even those.
No, I mean even the amount of latency it has, just because it's going into a codec and into a computer and back out again.
So what was the total latency of the hardware itself, even with sample based?
I knew this once because I measured it for somebody. But unless we can get on the internet and do a cunning search,
is it all codable?
it's. I believe it was a small number of milliseconds. I was surprised that it was as high as it was actually. What was it? I can't remember.
It's fair enough if you connect 5 of these units, then it will exceed 20 milliseconds, I guess. So it can be quite annoying.
It's something that you want to avoid.
Andrew, may I suggest that just so that we get an overview that I guess everyone's level of technology.
Yeah, sorry, I have some answers, so I'm satisfied.
It's absolutely fine. And perhaps we could have a quick introduction or a setup that people could interact with.
Oh yeah.
While you continue this discussion with Joel.
Yeah,
So
well, I was keen to actually compile one of these.
Level of interest.
Can I actually do the thing where I compile?
I'm just interested that the software goes, it does go beyond my understanding already.
Let me just grab some of these functions that the guy did. Blah blah blah. What did he do? He did some. This is this other guy's GitHub.
So you take a sample of the code here, copy and paste it into the environment and get it running.
That's what I'm going to do. So this is the code that the guys put up. Let's put it in. I'm actually in the right place. There we go. Where's it go? Where's it go? Is the code right down here? Sorry, just copied it off the repository, so it's not right here. Okay, that's the code that some random guy did. Let's get rid of that. I really don't know what this is going to do, so let's experiment.
So then you're compiling it and putting it in the
Compiling it and squirting it down to the hardware. Not sure what that's doing. It's well, let's plug an oscilloscope into it and see how it sounds. Whoa. Okay, so this guy's obviously into glitch. Ooh, yeah, look at that. No, I'm going to buy 2 of these now for that. Okay. That's kind of fun. Stick out.
So is this thing acting now as a generator or?
Yeah.
Is it,
So now, all we have now is that's disting straight into audio.
Okay.
And I'm just playing with that. I'm not quite sure if the inputs and outputs do anything in this algorithm. No. So it's basically generating something. So what I'm doing here is I'm plugging LFO into that control. Well, that gives you an idea anyway. So that's some brand.
That's cool.
I don't know where he got that code. He's all documented it.
I was getting into the groove.
It looks like some kind of. Well, yeah. Well, I'll tell you what. If we just stick a beat under that, then let's take an LFO this in time,
Yeah.
and then we can actually get jiggy with it.
This is going to go dubstep, I think. Great.
Yeah, it was dubstep. Very much so.
Well, okay. We'll stick it at 140 BPM then. No, that's not right. Wrong one. That one. Right, so my LFO is coming from here. Oh, that's the wrong one. There we go. Yeah. Mental. I think. Yeah, that's my next album. So there we go. So we've made music from code tonight. I feel we've succeeded in the Hackspace thing. So yeah. Does anybody? Shall I plug something in that people can just play with?
Yeah, I think
Why don't I put it back to normal? I put it back to its normal functionality.